Hi guys. Hope everyone's doing okay. Guess the plan is to try some videos here, and we're gonna kind of keep going on with some notes and things. Um, we're gonna utilize Google Classroom, and um, we'll just kind of see how things go. So really, what I want to kind of do today is I kind of want to keep going with what we were talking about last time in class, and we were talking about solutions and what a solution was, and we gave some examples and stuff like that. So let's just kind of get started. And the first thing that we said, what we were talking about, is we were talking about solutions, and we said a solution is just a homogeneous mixture of two or more substances in the same physical state. And we gave some examples of solid solutions and some gas solutions and some liquid solutions, and we talked about all that. And then we talked a little bit, we were working on solubility. And we talked about miscible versus immiscible, and soluble versus insoluble. And then at the end, we started talking about like dissolves like. Okay, and what we meant by that is a polar solvent will dissolve polar solutes. Okay, now a polar solvent is a molecule that is a polar molecule. So a perfect example of a polar solvent is H2O. All right, and it will dissolve polar solutes. All right, so again, the polarities are the same. So polar dissolves polar. Then we said nonpolar solvents will dissolve nonpolar solutes. Okay, so a nonpolar solvent, these tend to be like oil, gasoline, all right, and they'll dissolve like grease. Okay, they got to be the same polarity. Now, polar solvents, or water specifically, will dissolve ionic solids, but for a different reason. Okay, now remember, an ionic solid is really a salt. So do you remember why water dissolves salts? Right? Water will dissolve a salt by molecule ion attraction. And everyone forgets this one. Okay, and we talked about that in class. All right, so when we're talking about dissolving, polar solvents dissolve polar solutes, nonpolar solvents dissolve nonpolar solutes, and water, which is a polar solvent, will dissolve ionic solids because of molecule ion attraction. All right, and we did the lab in class. All right, so you should be working on that, and we'll talk later about when that's going to be due and things and how to do that. All right, but this is kind of where we left off last class. Now, before we get any further in solubility, I want to talk about liquid solutions. Okay, so not all liquids are solutions. Not all liquids are solutions, and you need to be able to figure out whether a liquid is a solution, is an aqueous, or not. All right, and there are some things that we look for. All right, so the first thing with a liquid solution is it has to be a homogeneous mixture. It's got to be a homogeneous mixture. If it's not, okay, if it's a heterogeneous mixture, it can't be a solution. So if you can see the parts, all right, it is not a solution. Solutions can have an odor. They can smell. They can give off a gas. That's okay. So, for example, what's a good example I can give you that gives off an odor? Well, gasoline is actually a mixture of nonpolar substances. So when we look at gasoline, we have different types of materials in there, and gasoline definitely has an odor. All right, gasoline's a solution. All right, so I guess that's an example of a solution giving off an odor. But if it does, that is okay. They don't have to, all right, but if it does, that's okay. Okay, they will not settle on standing. All right. Now what this means is that over time, the stuff that we dissolve in the solution will not settle down to the bottom. So for example, all right, if we take sand and water and we shake them up, right, the sand will kind of get suspended in the water for a little bit, but then it'll sink to the bottom. Okay, when it sinks to the bottom, that's what I mean by settling. All right, another example is a precipitate. Okay, so when we mix two liquids and they come together and they form a solid, all right, that solid will settle, which means whatever we made is not a solution. All right, so that's what I mean by settling on standing. Number 4, solutions will pass through a filter. Okay. And this is one that students miss all the time. All right, so if I take salt water, or NaCl aqueous, and I put it through a filter, like filter paper, okay? I pour the aqueous NaCl, the salt water, through the top. What do I get through the bottom? All right, well, it's not going to filter anything out. It's not going to filter anything. The salt water goes right through the filter. Oops. So let's say that I have some blue raspberry Kool-Aid, all right, and I pour it through the top of the filter. What am I going to catch on the bottom? Well, if it's a solution, the blue raspberry Kool-Aid will come out the bottom, and it will not filter anything out. And that's true. So if I pour Kool-Aid through the filter, it doesn't filter anything out. All right? Solutions go right through the filter. And our 5th one is one that I wish I could show you. If we were at school, I could. All right, but I'm not, so I can't show it to you because I don't have a laser. All right, but we can talk about it. Solutions are clear and do not disperse light. Now by clear, I mean you can kind of see through them, all right? They're not opaque. It doesn't mean they don't have color, all right, but they're clear. Now, what do I mean by dispersed light? This is the part that I would love to show you, all right? So if I have a laser beam, all right, so like a laser pointer, and I point it at the wall, the only place that you can see it is on the wall, all right? So the only place that we could see the laser would be right here. So if this is me with my laser, all right, I press the button, all right, and it sends the light over here, and the only place that I can actually see the light is on the wall where it's hitting. There's actually light waves here, though. I just can't see them. If I was to clap some erasers over this, okay, and the dust from the eraser came down here, it would actually show me the light beam from here to here. Okay, when I can actually see that light, it's dispersing the light. Okay, it disperses the light. Now, when all this dust is gone, again, I cannot see the light waves anymore. All right, and the only time I can see it is over here. Well, in a solution, solutions will not disperse light. Okay, solutions will not disperse light, which means the light waves will go right through them and we can't see them. If you can see the light waves, all right, if you can see the traveling light waves through the liquid, it is not a solution. So for example, if you take milk, okay, and you try to put a laser beam through it, you will actually see the light going through the milk because there are particles in the milk that disperse the light. Milk is not a solution, right? It actually disperses this light, right? So solutions meet all of these criteria, all right? So if they meet all of them, all right, it is a solution. Okay. All right, good. So let's talk about some things, and then we'll get into using table F. All right, so let's talk about temperature and solubility. First of all, as temperature increases, most solids, not all, are more soluble in liquids. So the example that I give this, that you may or may not have used or have seen, all right, is salt and water. And I don't know how many of you like salt potatoes, but I love salt potatoes, and I like as much salt as possible in the water when they cook them, because I like my salt potatoes really, really, really salty. All right, so when you buy the salt potatoes, all right, you're supposed to use a specific amount of water, and then you're supposed to use the whole packet of salt. And when you take the water and you put it in your pan and you dump the salt in and you stir it up, actually all of the salt will not dissolve. All right, it actually sits there on the bottom. But then you turn the heat on and you start heating up the water. And once the water is up to boiling at 100 degrees Celsius, if you actually look in the pot again, all of the salt has dissolved. All right, so over time, as the water is heated up, more and more and more of the salt in the water can dissolve. So as the temp increases, the solubility of the salt in water also increases. Right? And this is true of most substances. Right? Now, gases are a little bit different. As temperature increases, the solubility of a gas in liquids decreases. Now, this is pretty important. It's the exact opposite of our solids. Now, let's talk about this. So I don't know how much of you drink soda, all right, but there's CO2 gas dissolved in soda. All right, this gives us its kick. All right, and so we want to get as much carbon dioxide into that soda as possible. All right, so when it's made, when we make our soda, it's very cold. Okay, it's very cold because this will dissolve the most CO2 into the soda. All right, now, if you take a glass of soda, all right, so you pop the top, all right, you pour it into a glass, and if you happen to leave that glass on the table, all right, for a long time, okay, the temperature of that soda is going to go up, all right, and as that temperature goes up, the solubility of the CO2 goes down, and the carbon dioxide comes out of it. If you come back a couple hours later and you take a sip of that soda at room temperature, what's happened to the CO2? Well, a lot of it's gone, and it has become flat. And that's why this is happening. Okay. All right. The second thing I want to talk about is pressure insolubility. First of all, pressure changes have little effect on the solubility of solids or liquids. All right, so by changing the pressure, it really doesn't change the solubility of a solid or a liquid. But pressure has a major effect with gases. All right, so as pressure increases, the solubility of a gas in liquids increases. Okay, so if we have high pressure, more gas will dissolve into that liquid. All right, now, again, we can see this in a can of soda. All right, I don't know how many of you have ever done this, but you can do this at home. All right, if you take a can of soda and you pop the top, when you go, that's releasing that pressure, so the pressure is going down. If you quickly pour that soda into a glass, you're going to see it fizzing. Well, what's the That's the carbon dioxide coming out of the liquid. All right, we've decreased the pressure. All right, and once we've decreased that pressure, all right, solubility decreases and the carbon dioxide comes out. All right, pressure affects gases only. Okay, all right, good. Okay, now when we're talking about solubility, we can actually predict some things that are soluble and both insoluble in liquids. All right, and that brings us to table F. I hope you have a table F around. I hopefully have your reference tables. All right, and this is called a solubility table. Okay. And there's a couple things we do with table F. And really, it's used to help determine if a compound is soluble or insoluble in a polar solvent. Okay, now as soon as I say polar solvent, hopefully at this point you know that I'm talking really about water. All right, so this will tell us, okay, table F will tell us if a substance is soluble or insoluble in water. All right, so here's table F, and hopefully you have table F, because I want to look at it and I want to do a couple things. So what I want to do first of all is I want you to draw a line right here, right down the middle, because this is actually two different tables. And let's label this side F1 and this side F2. All right, now let's focus in on the F1 side. On this side, these are ions that are soluble. Okay, these are ions that are soluble in water. On the F2 side, these are ones that are insoluble. All right, so if we have these ions in here, all right, they will dissolve. These ions, they will not dissolve. Now, there are exceptions to both sides. Okay, so let's say we are in an exception on the solubility side. That means if we have one of these with a halide, that becomes insoluble, and then the exceptions over here where there are a lot of them, okay, these are soluble, okay, with the exceptions. All right, so this is two separate tables. Okay, we'll come back to this. All right, so how do we use this thing? Well, really the first thing we do is we got to figure out the ions. Okay, so we're going to figure out the ions. So let's say we have MgCl2. All right, our ions are going to be Mg plus 2s and Cl minus 1s. All right, so then what we're going to do, once we know what our ions on, then we're going to go to table F and look for the ions. Okay, so we go to table F. So we know for MgCl2, we got Mg plus 2s and we have Cl minus 1s. Now, remember, okay, this is a group 2. This is a group 17. Okay, so this is a halogen. Okay, this is a alkaline earth metal. All right, so remember that because that will help you. So let's take a look over here. We're looking for Mg plus 2 or Cl minus 1. Well, we know that neither one of them is a group 1. It's not ammonia. It's not the nitrate ion. It's not an acetate ion. It's not a hydrogen carbonate ion. It's not a chlorate ion. But all of a sudden, we have a halide. Halides are always soluble in water, except if it's with Ag, Pb, or Hg. Okay, if it's with one of those, it's insoluble. All right, ours is with Mg. All right, so chlorine, this is going to be soluble. Okay, so MgCl2 would be soluble in water. All right, let's try another one. Let's say we have NaNO3. All right, so we have Na pluses and NO3 minuses. And I want to know, is this soluble or insoluble? All right, well, we go back to my table. All right, we immediately know, okay, that Na is a group 1 ion. There are no exceptions. All compounds with a group 1 ion are soluble. All right, we could also look at this one. Nitrates, they're also always soluble without exception. So in both cases, all right, this is going to dissolve in water. All right, so this is soluble. All right, let's look at, let's try BaCrO4. So we have Ba plus 2s and CrO4 minus 2s. All right, so here we go. All right, now we have to go looking for the different ions. All right, Ba, okay, group 2 is not on there anywhere. Group 2 is not on there anywhere. So let's look at CrO4. Okay, chromate, here it is. Okay, so chromate is on the insoluble side. So okay, these are usually insoluble. Now, if it's with calcium, magnesium, or ammonium, it would be soluble, but it's only with barium. All right, so that is not an exception. So this would be an insoluble compound in water. Okay, this would be an insoluble compound. Okay. Now, let's say we have, let's do another one. How about, let's say we have CaOH2. So we have Ca plus 2s, okay, which are group 2, and we have OH minus 1, and remember this is a hydroxide ion. And I want to know if this will dissolve in water. All right, well, the Ca, or the group 2, is nowhere on here, all right? But hydroxide is, and it's on the insoluble side. All right, so normally hydroxides are insoluble. There are a few, though, okay, that are soluble. And calcium is one of those exceptions this time. So this would be soluble, okay, in water. Okay. Hopefully this helps you with table F. Right? Now we're going to use table F for something else. All right, there's another big thing we can use table F for. We can predict if a reaction will occur when two ionic solutions are mixed. When we say ionic solutions, we're talking about salts dissolved in water. Okay. So when we have two ionic solutions, we can predict if a reaction is going to occur or not. A reaction will occur if one or more, it just needs to be one, but it can be more of them, one or more of the products are insoluble. Okay. A reaction will occur if one or more of the products are insoluble. Let's star this. And I want you to underline products. Not reactants, we're talking about products. And we're going to end up using table F again. Okay. So let's say we have something like this. Silver nitrate and sodium chromate solutions are mixed. Will a reaction occur and why? Okay. All right, now as soon as you see solution, okay, that means these things are dissolved in water, right? They are aqueuses, all right? So now, before we can actually do this, we need the formula for this and the formula for this, and we're going to crisscross. So silver is Ag, which is +1. Okay, nitrate is NO3, which is -1. Comes over here, and we have AgNO3. It's in solution, which means it's dissolved in water, so we need to write AQ. Okay, we are reacting it with sodium chromate. Well, sodium is Na, which is +1. Chromate is CrO4, and it's -2. This comes over here, and this comes over here, and we end up with Na2CrO4. And again, it's dissolved in water, so it is an aqueous. Now, hopefully at this point you can already tell that this is going to be a double replacement reaction. The positive of the first is going to go with the negative of the second. Positive of the second is going to go with the negative of the first. All right, and we're going to crisscross those together. All right, here we go. So we have Ag, which is +1, and we are going to crisscross it with CrO4, which is -2. This comes over here, this comes over here, and we get Ag2CrO4. And the other one is going to be crisscross between Na and NO3. +1, -1. And our second product is NaNO3. Now, I want to know, does this reaction take place? All right? In other words, okay, do we get something that's insoluble? And it's got to be one of these. Now, all these are soluble. All right? We don't even need to worry about this. We're worried about the products. All right? So let's look at NaNO3. If we go to table F, okay, here's Na right here. It's on the soluble side. So we know this is soluble, which means it's going to stay in the water, which means this is going to be aqueous. It's not going to come out. Right, now let's look at AgCrO4. Well, chromate is on the insoluble side. There are some exceptions. It's not a group 1, it's not a Ca, it's not Mg, it's not NH4. All right, so silver chromate is insoluble. It's insoluble, which means it's going to form a solid. Okay, it's going to form a precipitate. Okay, it forms a precipitate. That precipitate wasn't there before. It's something new, which is telling us that a chemical reaction is occurring. This is going to form a solid. All right, this reaction occurs because it produces one insoluble compound. All right, so the rule is at least one has to be insoluble. It could be both, but it just has to be at least one. So this reaction happens or occurs because Ag2CrO4 is insoluble. Okay, and it forms that precipitate. Okay, so this is where we're going to stop for today. All right, this will be posted right along with some work that I'm going to give you on Google Classroom. All right, so for now, we've started that lab. I want you working on that lab. We got to figure out what we're going to do to turn it in. Just hang tight with that, so work on it. I've given you some other work that you need to be working on also. All right, I gave you a poster on the 4 intermolecular forces. All right, so I want you to use a piece of paper just like this. All right, and using pictures and words, I want you to demonstrate your 4 intermolecular forces. So you're going to talk about hydrogen bonding, dipole-dipole, van der Waals forces, and molecule ion attraction. All right, so I don't care how you do it. You can set it into sections. All right, but I want you to make a little poster showing me some pictures of each, describing them, and so on and so forth. And probably I'm going to have you take a picture of it and submit it to Classroom. All right, doesn't have to, don't worry about, hopefully you'll have it in the next couple days. We'll figure out due dates. All right, I'll probably give you a couple days to do it. All right, so please pay attention to Google Classroom. All right, I'll do another lecture probably tomorrow, and hope everyone's healthy, and we will see you in the next video.